Right. Can you hear me? Right. Okay. Right. Uh, all right. Now this is the plan. Now, uh, we'll discuss this Doppler effect remaining questions as soon as possible. Then tomorrow we can start a new section. So plan right now is completing remaining Doppler effect questions. Right. Okay. Now, right. Okay. Uh, right. Now we'll discuss question number 18. Question number 18. Doppler effect tude questions. Doppler effect tude questions. Now this question number 18. 18. Now it says that two trains with a velocity of 34 ms minus 1. Two trains with a velocity of 34 ms minus 1 moving towards each other. Moving towards each other along two parallel tracks. Along two parallel tracks. Capital A train emits a sound of frequency 500 Hz from its horn. What frequency does the driver of the other train hear? What frequency does the driver of the other train hear? Does the above calculated frequency change due to wind blowing parallel to the railway track at a speed of 50 ms minus 1 toward the second train? If so, how much is it? What will be the answer if the wind blows in the opposite direction? Now there are two trains in two parallel tracks. Two trains are moving towards each other. Right. Now let's say now this is my second train. This will be my first train, train number one, right? Now both of them move in parallel tracks and they are moving towards each other. Now they mentioned the velocity of each train is 34 ms minus 1. Velocity of each train is 34 ms minus 1. 34 ms minus 1. Now this train is also moving with 34 ms minus 1. 34 ms minus 1. Right, okay. Train number 1, train number 2. Right. Okay. Then let's say now train number 1. Let's assume train number 1 emits a sound of frequency 500 hertz. This train number 1 emits sound waves of frequency 500 hertz. In the question they are asking what is the frequency heard by the second train. Now first train produces sound of frequency 500 hertz. They are asking what is the frequency heard by the second train. Then we can clearly say that first train is our source, second train is our observer. But this time our source and observer both of them are moving. First train, that is my source. Second train, that is my observer. Observe. Then what's happening now? Source and observer both of them are moving towards each other. Source and observer both of them are moving towards each other. Then what is the equation? I know actual frequency of the source is 500 hertz. I want to find the apparent frequency heard by second train. I say F1. Actual frequency simple if apparent frequency heard by this train is I say F1 apparent frequency. Then we can write down. F1 equals simple if. Now this time now source and observer both of them are moving towards each other. Then what can you say about the numerator? V plus V naught over V minus Vs. You can remember these equations. Then we can say that now F1, this is what I need to find. If actual frequency of the source is 500 hertz, 500 hertz, then V, velocity of sound waves. Now it must be 340. Now if they didn't give velocity of sound waves, I said to consider 340 ms minus 1. 340 plus, now V naught. Now my observer, that is second train. Velocity of second train is 34 over over V means again velocity of sound 340 minus velocity of the source. Now source is my first train, its velocity is 34. Then we are getting 500 into 340 plus 34. 374. 374 over 340 minus 34. How much? 306. 306. So in this case, we will obtain apparent frequency heard by the second train will be 500 into 374 over 306. Then when we simplify this, what will be the answer? Then when we simplify this, what will be the answer? Now use log simplification. If we simplify this, we are getting 374, 306. Then we are getting roughly 611.11 hertz. 611.11 hertz. That is my F1. Then first part is done. Two trains with a velocity of 34 ms minus 1 are moving towards each other along two parallel tracks. Capital A train emits a sound of frequency 500 hertz from its horn. What frequency does the driver of the other train hear? That is 611.11 hertz. Now we understood that idea. That's okay. Then further they are asking, does the above calculated frequency change due to wind blowing parallel to the railway track at a speed of 15 ms minus 1 toward the second train? Yes. Now they mentioned that now there is a wind, that wind is blowing parallel to the track towards the second train. Wind is blowing parallel to the track towards the second train. In that case, if I draw the wind, this will be the direction of wind towards the second train, parallel to the track. Then I say that velocity of the wind is capital W. Velocity of the wind is capital W, that is 15 ms minus 1. Then we know that now, obviously, what will happen? When there is a wind blowing parallel to the track towards second train, obviously F1 value will change. Obviously, F1 value will change. So therefore, answer is yes. Then they are asking, if so, how much is it? When there is no wind blowing towards second train, apparent frequency heard by the second train is 611.11 hertz. Now, when there is a wind blowing towards second train, what will be the apparent frequency heard by the second train? Now, very similar equation. The only difference is you want to check, because I told you, I explained that when there is a wind, it will impact for the velocity of the sound. Suppose if the direction of wind is in the direction of sound, then what is the velocity of the sound relative to the observer? V plus W. If the direction of the wind is opposite to the direction of the sound, then what is the velocity of the sound relative to the observer? V minus W. Now here you can clearly see that direction of sound wave propagation. Sound propagates to the right side direction. Then what is the direction of the wind? Wind also blowing towards right side direction. Then this wind supports the motion of sound waves. Then here capital V means velocity of the sound. Now we substitute 340. When there is a wind in the direction of sound wave propagation, then we want to add W for this capital V. V is 340. Now this time we have to add capital W also to this V. In that case, we write the equation. In that case, right? I say now frequency is F1 dash, that is equals to same equation if now here V plus W, here V plus W, here V plus W plus V naught over here instead of V we are adding W, V plus W minus Vs minus Vs. So then in that case our F is 500. F is 500 into my V will be 340. W means it's 15 plus V naught, that is 34 over here again 340. W means 50 minus 34. When you simplify this, you will get the answer, right? You will get the answer. So then we are getting 500 into 340, 34, 374 plus 15, 384, 389 over 340 minus 34 means 306 plus 15, 316, 316, 321. Then I am getting F1 dash. F1 dash. Now that means apparent frequency heard by the second train when wind blows in the direction towards the second train. In that case, F1 dash equals 500 into 389 over 321. So when you simplify this, you will obtain 500 into 389 over 321. 605.92. 605.92. 605.92 hertz. F1 dash. Then next, further they are asking now, rather than wind is blowing towards second train, if the wind is blowing opposite to the direction of second train, that means this time wind is blowing not to the right side direction, this time wind is blowing to the left side direction. In that case, what will be the apparent frequency heard by the second train? Then what is the only difference? Now I told you that if wind is blowing in the direction of sound waves, we have to consider V plus W instead of V. Now what is V here? Here V means velocity of sound. When wind is blowing in the direction, when the wind is blowing in the direction of sound waves, instead of capital V, velocity of sound, we have to consider V plus W. When the wind is blowing in the opposite direction of the sound wave propagation, then we have to consider instead of capital V, we have to consider V minus W. The only difference here is again not V plus W this time. This time V minus W. Why? Opposite. The next case, I say F1 double dash equals F V minus W plus V naught. V minus W. Instead of V, I am substituting V minus W. Minus V's. So then if I substitute the values, f is 500, f is 500, my v will be 340 minus 15 plus 34 over 340 minus 15 minus 34, right? So then when we simplify this, we are getting 500, 340 plus 34 means 374, 374 minus 15, 364, 359, 359, 359 over 340 minus 34 means 306. If I further subtract 15, 300, 291, 291, 291, 291. Then I'm getting F1 double dash equals. If I simplify this, I'm getting 500 into 359 over 291, 616.84, 616.8 hertz. F1 double dash. Raise your hands if you understood. Raise your hands. If you understood, raise your hands. All right. Then 18 discussed. 17 discussed in the class. 16 discussed. 15 discussed. 14 discussed. Right. Now we'll come to question number 12. Question number 12. So in that case, it says that a tuning fork vibrates at the frequency of 512 hertz and is dropped from rest by a person on the top of the building. If the tuning fork falls freely, find the position of the tuning fork. Find the position of the tuning fork. That means displacement of the tuning fork. When the person on the top of the building hears a frequency of 480 hertz. A frequency of 480 hertz. Now this time. Question number 12. 12th one. Right. Now that's a building. Tuning fork is dropped from a building. Right? Tuning fork is dropped from a building. Right? Now let's say now there is a person observing from standing on the top of the building. The person dropped the tuning fork. This person dropped the tuning fork. Right? Then initially, when the moment the person drops the tuning fork, initial velocity of the tuning fork is, we know that that's 0. When the moment the person drops the tuning fork, we know initial velocity of this tuning fork will be 0. Right? 0 m is minus 1. But this tuning fork is moving under gravity with a vibration. Now, what is the natural frequency of the tuning fork? That is 500 hertz. Now, here at this moment, you can understand that when the moment the person drops the tuning fork, there is no relative motion between the observer and the tuning fork. Observer also at rest. Tuning fork is also at an instantaneous rest. 0, 0. Then what is the frequency heard by the observer? Actual frequency of the tuning fork. Now they mention tuning fork vibrates at a frequency of 512 hertz. Then actual frequency of the tuning fork is, we know that. Actual frequency of the tuning fork is, we know that. 512. 512. Right? 512. Right? Now what would happen? Now we know that when we drop this tuning fork under gravity, what would happen to the tuning fork? Velocity of the tuning fork gradually increases. Then what would happen? Observer is at rest, but tuning fork is moving further under gravity. Observer is at rest, but tuning fork is moving under gravity. The velocity of the tuning fork gradually increases. That means there is a relative motion between the tuning fork and the observer. There is a relative motion between the tuning fork and the observer. Now they mentioned at a particular instant, at a particular instant, apparent frequency heard by the observer. Apparent. Now this time, who is my source? My source is tuning fork. My observer is the person. Now they mentioned at a particular instant, apparent frequency heard by the observer is 480 hertz. Right? Right. When the tuning fork is somewhere here. Now actual frequency is 512 hertz. Simple. If is we know 512 hertz. But at this particular instant, when the tuning fork, now this tuning fork is keep on falling down, at this particular instant, apparent frequency heard by the observer is 480. 480. I say if one is 480 hertz, then we know who is our source. Our source is tuning fork. We know tuning fork is our source. Tuning fork is our source. Who is our observer? The man is the observer. Man is the observer. Observer. Then what we can do? Now it seems like observer remains stationary. Source is moving away. Source is moving away. Then what is the equation between apparent frequency and actual frequency? The equation will be apparent frequency f. Now source is moving away. Source is moving away. Then we are getting apparently source is moving away. Observer is at rest. So therefore V over V plus Vs is the equation. This is the equation. Now understand velocity of the sound must be 340 in this case also. Velocity of the sound must be 340 ms minus 1 in this case as well. Now 480. F1 means now F1. F dash means F1. F1 is 480. F means we know that 512. Capital V 340. 340 velocity of the source, velocity of the tuning fork at this instant. Velocity of the tuning fork at this instant. Plus Vs. Vs. Right? Then subjecting 340 plus Vs equals 512 into 340 over 480. Then when I subject Vs, my Vs will be 512 into 34 over 48 minus 340. Then I'm getting a answer, this type of answer. Then I'm getting 512 into 34 over 48 minus 340 minus 340. 22.67 ms minus 1. 22.67 ms minus 1. Okay. 22.67 ms minus 1. But they don't ask now. Now we know that this tuning fork's velocities keep on increasing from 0. 1 ms minus 1, 2 ms minus 1, 5, 10, 15, 20. Now exactly at this instant, when the moment observer hears 480 hertz apparent frequency, velocity of the tuning fork is 22.67 ms minus 1. But they are asking not the velocity, they are asking the displacement to the tuning fork. When the moment observer hears 480 hertz frequency, apparent frequency, what is the displacement achieved by the tuning fork? That's what they are asking. Now hereafter we can apply linear motion equations. Now I know V is, I know initial velocity is 0. Tuning fork falls under gravity. Gravitational acceleration is capital G, 10 ms minus 2. Initial velocity, final velocity, acceleration. I want to find displacement. What is the best equation? V squared equals u squared plus 2as. Downward direction we can apply. V squared equals u squared plus 2as. Then what is my V? My final velocity is 22.67. 22.67 whole squared. Initial velocity of the tuning fork is 0. Acceleration 10. Displacement will be capital S. Capital S will be 22.67 whole squared over 20. This will be our S. In that case, if you simplify this, what is the answer? If you simplify this, 22.67. Now you use log, okay? Now I don't have time to do the simplification. 25 point, it's roughly 25.7. 25.7. Roughly S equals 25.7 meters. Right, in that question is also discussed. Then we discussed 12. Then we didn't discuss 13. We'll discuss 13 later. I think question number 1 to question number 3 discussed. Okay, we'll come back to question number 4. Sorry, we'll come back to question number 5. Question number 5. Question number 5. Question number 5. Right? 5. Now, this time now, certain line in the emission spectrum of distant star. Now, stars. Now, it's not like now. I told you the Doppler effect occurs not only in the sound sources. Doppler effect occurs not only because of sound sources. It's not common for sound waves, but also it is common for all type of waves. Even electromagnetic waves, Doppler effect occurs. Now that's a star, right? There is a star. They mentioned that this star is emitting electromagnetic waves. Okay, there's a star. That star is emitting electromagnetic waves. Now there is a stationary observer. That stationary observer is observing the motion of the star. There is a stationary observer. He is, let's say, standing on the earth and he is observing the motion of the star. But the star is emitting electromagnetic waves. Now, after now, all the previous questions we considered sound waves. Sound waves. All the time, propagation of wave was the sound waves. But this time, our wave is not sound waves. Our wave is electromagnetic waves. Doppler effect is common for sound waves as well as all types of waves, including electromagnetic waves. Now, that star, it is moving. When that star is moving, it emits electromagnetic waves. Then we can clearly see that who is our source? That star should be our source. Why? Because that star is emitting electromagnetic waves. So therefore, our source is the star. Our source is that star. The star is moving. That means our source is moving, but we don't know exactly to which direction. Source is moving towards the observer, or source is moving away from the observer. We don't know, right? But we know this observer is stationary. That's a stationary observer, right? Stationary observer. Star, right? Now here is our stationary observer, right? So star. This is our man, right? But they mentioned certain line in the emission spectrum of a distant star measures 600.8 nanometer in wavelength. Its actual wavelength is 600 nanometer. And all the previous questions, they have given actual frequency and apparent frequency in terms of frequencies. But this time they are talking about actual wavelength and apparent wavelength. Now we can remember the equation that we learned in properties of waves. V equals F lambda equation. Because these are electromagnetic waves. This star is emitting electromagnetic waves. What is the velocity of the electromagnetic waves? 3 into 10 to the power 8 ms minus 1. And if we know the wavelength, obviously we can find the frequencies. Now they mentioned actual wavelength. Look at it. Actual wavelength of the electromagnetic wave emitted by the star is lambda. Apparent wavelength heard by the observer, that is lambda dash. Now what is the value of lambda? Now lambda is 600 nanometers. 600 nanometers. Then what is the lambda dash value? Lambda dash will be apparent wavelength, that is 600.8 nanometers. Then let's say the corresponding actual frequency is simple if apparent frequency is f dash. Now this observer is stationary observer. Stationary observer. Stationary observer. But we don't know exactly which direction this star is moving. Now the star is the source. We don't know exactly what direction the source is moving to the observer or away from the observer. We don't know. But by looking at the apparent wavelength and actual wavelength, we can easily decide the direction of the motion of the star. Now look at it. Now we know that according to V equals F lambda equation, the velocity is always constant. When wavelength increases, frequency decreases. When wavelength decreases, frequency increases. We learned that idea. Now look at the actual wavelength and apparent wavelength. Actual wavelength is 600. Apparent wavelength is 600.8. That means apparent wavelength has increased. Comparing with actual wavelength, apparent wavelength has increased. Then what can we say about the apparent frequency? If apparent wavelength has increased, if apparent wavelength is higher than actual wavelength, what can we say about the apparent frequency? Apparent frequency must be lower than actual frequency. You understand now? Apparent wavelength is higher than actual wavelength, then apparent frequency must be lower than actual wavelength. Apparent frequency must be lower than actual frequency. Then if your apparent frequency is lower than actual frequency, if your apparent frequency is lower than actual frequency, star is moving towards the observer or away from the observer. Reply in chat box. If the apparent frequency is lower than the actual frequency, if the apparent frequency is lower than the actual frequency, star is moving towards the observer or away from the observer. Reply in chat box. Now we know apparent now. Apparent wavelength is larger than actual wavelength. Then we know apparent frequency must be smaller than actual wavelength. Then I'm asking, by based on this frequency inequality, we can come to a conclusion about direction of motion of the star. It's moving towards or away. Reply. It's moving towards or away. If your apparent frequency is lower than actual frequency, if your apparent frequency is lower than actual frequency, reply in chat box quickly. Why I am getting only one answer? Quickly, quickly. At least one student or two students just reply in the chat box because we don't have time to discuss. Away. If apparent frequency is smaller than actual frequency, yeah, the star is moving away. That's the idea. Away. V's. Then they are asking, is the star is moving towards the observer or away from the observer? Yeah, away from the observer, obviously. Then they ask, calculate the speed of the star. Very easy. What is the equation? Observer is stationary, source is moving away from the observer. Then the equation will be f dash f v v plus v is. Now this time not the velocity of sound waves. These are electromagnetic waves. Here capital V means velocity of the electromagnetic waves. Here capital V means velocity of the electromagnetic waves. Understand that idea. Now I don't know apparent frequency. I don't know actual frequency. But I know apparent wavelength and actual wavelength. Look at it. Now when I use V equals F lambda equation, right, I can write down F means V over lambda, right? Apparent frequency F dash means V over apparent wavelength. Actual frequency F means V over actual wavelength. Instead of F dash and simple F, I'm substituting these two. V over lambda dash equals F means V over lambda, right? Sorry, here V means rather than using V, velocity of electromagnetic waves, we can use V. Yes, V. Yes, V. Then into V over V plus Vs. Now I need to find Vs. Velocity of the star. Then here capital V cancel out. Then if I cross multiply, I am getting V plus Vs. V plus Vs. If I bring this one here, V plus Vs. V lambda dash over lambda. V lambda dash over lambda. V lambda dash over lambda. Now substitute. Then Vs equals 3 into 10 to the power 8 lambda dash. Lambda dash means 600.8. 600.8 10 to the power minus 9 over lambda. 600 to the power minus 9 minus V. 3 into 10 to the power 8. So then we can cut minus 9 we can cut. Then we are getting right. When you simplify this, you will get the answer. They are asking me, isn't it? When you simplify this, you will get the answer. Then that question is also discussed. That question also discussed. Raise your hands if you understood this question. If you understood this question, raise your hands. If you understood, raise your hands. Then that is also done. Then 5 done. Right. Now 6 discussed in the class. We discussed 1, 2, 3. We didn't do 4. Now we done 5. 6 also discussed in the class. 7. 7. Right. 7, 8, 9. 7, 8, 9. 7, 8, 9. Right. 7, 8, 9. So give me a second. Give me a second.